Darn it, my battery ran out again. So this is part 2. Shouldn't be too long. We're going to finish this problem and do an FRQ or two and be done. So maybe 10 minutes at the most. So I was applying that reverse property here of, but it's not going to help because sorry, I should finish my sentence. I'm applying the reverse property of exponents here, but it's not going to help in this case. We did it last time because the second part after our addition had an ln, and I knew an e to an ln was going to cancel and just come out to be a 2. Here that's not going to happen. It's just going to stay as e to the 1/2, so it's not particularly helpful. So we're just going to stay at this part here. And now here's where we're going to separate into our two different choices. So it could be y minus 1 equals e to the negative 1 over x plus 1/2. Or it could be the negative version of our absolute value part. All right, so what that means is over here again, I'm just going to essentially multiply both sides by negative 1. So here I've got y minus 1. It's already good to go. I want to solve for y. So e to the 1 over x plus 1/2. I'm adding 1 to both sides. I'll just stay with this side. Let's check our initial conditions. So our initial conditions again were 2, 0. So if I plug in 0 for y and I plug in 2 for x, does it work out? So I get 1. So I'm getting e to the 0 plus 1. I'm getting 0 equals 1 because e to the 0 is 1. So this does not look like our choice. It's going to be this guy, so let's solve it for y. So y minus 1 equals negative e to the negative 1 over x plus 1/2. I add 1 to both sides. I get negative e to the negative 1 over x plus 1/2 plus 1. Our initial conditions were 2, 0. So let's confirm that they work. I plug in 0 plus 1/2. So I get negative e to the 0 plus 1. E to the 0 is 1, so I'm getting negative 1 plus 1. 0 equals 0, checks out. That's our winner. Let's write it in function notation. So where was the y equals 1? Negative e to the negative 1 over x plus 1/2. Good times. Let's look at an FRQ that was one of these. This one's a little hard to read, but it's the differential is defined as dy dx equals 3x squared over e to the 2y. All right, so part A says find a solution y equals f of x to the differential equation that satisfies the initial conditions that f of 0 equals 1/2. Okay, and so what we want to do here is we want to start by I'm just going to recopy it. Separate our variables. So if I multiply, I'm going to cross multiply here and get e to the 2y dy equals 3x squared dx. Looks like the variables are separated. Y is on one side, x is on the other. So now we're going to go ahead and integrate both sides. So this guy looks like a composition function, right? I've got an outer function and an inner function. 2y is plugged into e. So what I need to see is the derivative of the inner function out here times that. So the derivative of 2y is 2. So I want to see a times 2 there for this to work. I can add that. I can multiply by that constant in there as long as I multiply by a constant outside that's going to kind of keep it. It was a 1, so it's got to kind of bring it back there. If you recall that from the last section. Equals the integral of 3x squared dx. So now that I've got this one prepped to be reverse product rule, reverse chain rule, 1/2 comes along for the ride. And the integral, the antiderivative of the outer function. So 2y was the inner function. E to the y is the outer function. The integral of e is itself. And I do have to recopy that inner function there. So that's going to work out to be 1/2 e to the 2y. Okay. And on the other side, we get equals power rule. So it's going to be x to the third plus c. So now that is going to be our general solution. Now we want to use our initial conditions and look for our particular solution. So I'm going to say, what was it, 0, 1/2. So I'm going to put in 1/2 for y. And 0 for x. Solve for c, and I get 1/2 e to the first, right? So there we go. So our c is going to be equal to 1/2 e. So our particular solution is going to be 1/2 e to the 2y equals x cubed plus 1/2 e. Remember, 1/2 e is a constant, just like pi is, just like sine of 2 is, just like ln of 4 is. Those are all just constants. All right, so now we want to solve for y. So we're going to multiply both sides of the equation by 2. We're going to take the natural log of both sides. Remember, our initial condition, we're plugging in 0 for x. So I'm going to get 0 plus e. That's a positive number, so I don't have to worry about the absolute value here. I'm going to divide both sides by 2. I'll write it like this. And I like to write it in function notation. I think it doesn't matter in terms of an AP reader. So that's part A, I believe. Remember, this is a 9-pointer, so that's 6 points for doing that. Find a solution to the differential equation satisfying. So we did. There's our particular solution. Part B, find the domain and range of the function. So in this case, they're just kind of seeing if you know what the graph of a natural log looks like. So the domain of a natural log, I was saying the input part, the part inside the natural log, I've said before, it has to be positive. So you take the inside part, 2x cubed plus e, has to be bigger than 0. It cannot be equal to 0 because the natural log, the inside part, has to be positive. So if I solve this, equation for x, that's going to be the domain of my function. That'll force the inside part of the logarithm to be positive. So I subtract e from both sides. I divide by 2 on both sides. So I'll get negative e over 2. And then I cube root both sides. And that would be my domain. So you might want to say okay, so it's all the x's that are bigger than that number there. And then we want to do our range. So you have to know what the range of a log function is. All we have going on here is multiplying it by 1/2. So if you know that the natural log function looks like this, when you're thinking about range, the only thing you really have to worry about, well, it would always be all reals, I guess. So when you're multiplying by 1/2, it's not going to change that, right? If you think of the range of this function, it goes down forever and up forever. You have to remember that even though it looks like it's flattening out here, it's not. It's just slowly, it's very, very slow growth. Okay, so the range is going to be all reals. That's just sort of kind of your knowledge of functions, of the log function. So the range is going to be all the y values that are bigger than negative infinity but less than infinity. All right, let's see. What else do we have? Oh, we're on to our next section. So that's it. Thank you.